the problem that is given that G is a group and it is having a property that for any two elements A, B in G, A dot B raised to the power I is A to the power I dot B to the power I. This dot is the binary operation of the group G, and this happens for three consecutive integers I, and this property holds for all A, B in G. Then we have to show that G is Abelian, G is commutative. This problem is an interesting problem of the book IN HERSTEIN, section 2.3, and this is the problem number 4. So let us see how we can show that. So what we have given, G dot is a group, and for all elements pairs in G, this happens xi raised to the power I minus 1. These are quite obvious what is the meaning of xy, that is x dot y. So we are omitting that. Xy raised to the power I minus 1 is given, x to the power I minus 1 dot y to the power I minus 1, also given xy to the power I is x to the power I y to the power I, also given x to the power xy to the power I plus 1 is x to the power I plus 1 y to the power I plus 1, because this happens for three consecutive numbers I. So we take the three consecutive numbers are I minus 1, I and I plus 1, and this happens for all xy belongs to Z. Okay, so for I plus 1 the property holds. So what we can write, xy to the power I plus 1 is x to the power I plus 1 y to the power I plus 1. So we are starting with this. So from this we can write, this is like xy dot xy to the power I, right? Xy means x dot y, and this dot is a binary operation for the group G, and for right hand side we are writing the same thing. Okay, fine. Now if we apply the property for the integer I, we can rewrite this like xy dot x to the power I y to the power I, and right hand side as it was, right? And this is because property holds for I also, right? Okay, so we reached this stage. Fine. Now what we'll do, we'll break this part in this fashion: x to the power I minus 1 y to the power I minus 1 y. We can write this just the binary composition of elements in group G, and right hand side we'll write x to the power I plus 1, and this we shall write y to the power I plus 1. For this we can write this, right? Okay, now as xy belongs to G, we have inverse, so for these elements. So if we compute, if we uh, if we do the binary composition with the inverse, say in the next step, as y belongs to z and g is a group, so y has inverse, that is y inverse, and we are composing y inverse from the right. So in that way these two terms gives the identity, so these two terms gets cancelled out. So let's cancel this. Okay, so finally we get this. Okay, fine. Now see for this part, x to the power I minus 1, y to the power I minus 1, we can replace this by xy to the power I minus 1, because this property holds for integer I minus 1 also. So we will replace this in this fashion, so it will become xy x and xy to the power I minus 1, and in the right hand side it was this, right? Okay, so this happens because the property holds for integer I minus 1. Okay, fine. Now what we will do, we will recalculate the right hand side, and what we will do is we'll write this like x to the power I plus 1, we can write this, right? And for this part we will apply the property for integer I, so this will become this. Okay, fine. Again we can write this as x into xy into xy to the power I minus 1. Basic binary composition in group. We are just using the properties for the group G, and we are not commuting any elements, right? Because we will prove the group is commuting, so we don't have the choice to commute the elements. So we are just using the property of group, we are using the composition binary composition rules in the group G. So what we basically get, xy xy to the power I minus 1 is xy to the power I minus 1. Now again x belongs to z, y belongs to z, so their I minus 1 times composition will also be in G, and as G is a group, so it will have a inverse for this element. So the inverse, we can write the inverse like minus I plus 1, so we'll compose xy to the power minus I plus 1 from both sides. So in that way these terms gives identity, right? So we can replace this by 1. So we are just replacing. So finally we get this xyx is xxy. Now we can again we can, what we can do, we can compose x inverse from the left, because x is element in G, so these two terms give identity. So finally it will become yx is equal to xy, and this happens for all xy in G. So this implies G is commutative.